like 1 over r, correct? But in the dipole case, it drops like 1 over r squared. This is something that you need to think about and have it handy all the time. This is an important concept. So for the Coulomb field, the electric field drops like 1 over r squared. The potential drops like 1 over r. But for the dipole field, the potential drops like 1 over r squared. Okay, now let's try to see what happens with this new thing that we just obtained here. What about the electric field? The electric than the potential, and it's also more complicated than the electric field produced by a single charge. You can see this is a little bit more messy than a single charge. The first term is not really that bad. The first term of the electric field tells us the following. This term tells us that the electric field, this term, not the whole thing, but this term, points in the direction of the dipole moment. Right? Because we have a p up here and everything else is a scalar. On top of that, this first term drops like r minus r prime cube. So it drops that like the distance cube. Okay, so for the Coulomb field, the electric field drops like 1 over r squared. For the dipole, at least the first term drops like 1 over r squared, number 1. Okay? And this first term points in the direction of p. So I come back to this one. What about the second term? This is a little bit more complicated. But there is a p dot r minus r prime, similar to that one we were just discussing. So if you work it out, it's going to be the magnitude of p times the magnitude of r minus r prime times some cosine. Right? The magnitude of r minus r prime cancels with this one, and then we get 1 over the magnitude of the fourth. And if we compute the magnitude of this thing, it's going to be the magnitude cube down here. So this term and this term, both of them, drop like 1 over the distance cube. Okay? I want you to think about carefully all that I'm saying, okay? And then this term is a little bit trickier. This term, maybe you can help me with that, okay? So I claim, or I showed you, that this first term points in the direction of p. What about this term? This term points in which direction?
Same, because it's a projection, because it's a direction.
Just look at the thing. Where is the vector here? Sean?
It's the direction of r minus r prime.
Yeah, this is the direction. Okay? So if I actually now think what's going on with that electric field, it's really messy, because the electric field of a single charge, the Coulomb field, very easy to describe, drops like 1 over r squared, and I go to that point and it points in the unit vector in the radial direction, and we can go home and, you know, we can understand that in high school. This is a little bit more complicated. Let's say that that is where my dipole is. Okay? And let's say that I'm going to exaggerate. Let me draw the dipole moment like that. Okay? And now I'm going to make an observation somewhere. This, of course, is r minus r prime. So this term is no problem. This term, the second term, I can rewrite it as minus 3 times p dot r minus r prime divided by r minus r prime to the fourth times r minus r prime divided by r minus r prime. I wrote the same thing exactly, but now I know that this is a unit vector, like before. Okay, so this tells me that this second contribution to the field is in this unit direction, and it has a magnitude equal to all this thing here. Okay, which again, if I expand the scalar product, I'm going to get p r minus r prime and a cosine, so it's going to be p cosine divided by cube here. Okay, so both the first term and the second term drop like the distance cube, this distance. Okay, and so I have two contributions. The second contribution points with a negative sign. Yes, it's a -3. So it points like that. That's the second contribution. And what about the first contribution? The first contribution is in the direction P. So that's, okay, so that the direction P is this one. So it's going to be like that. So that means that at any point in space, there are going to be two contributions. Each one of them drop like the distance cube with respect to the source. And there are two vector contributions that need to be added up to get the full electric field at that point. One of them is a radial component that is attractive, and the second one is a component that is in the direction of P. Okay? Of course, that there is a slightly additional thing that complicates the description because we have a scalar product, and this is related with what I said for the potential before. There are cases in which the scalar product is going to make it 0, P dot r minus r prime. So in general, I write P times the cosine of the angle divided by this cube. But when the top is 0, then that term doesn't contribute. Okay? So again, when is that 0? Is when r minus r prime is perpendicular to P. And that happens in this plane. On that plane that passes through P, all the points on that plane are perpendicular to P, right? If I have a vector here perpendicular to this table, all the points on this table are perpendicular to P, so r minus r prime dot P is equal to 0. So this is a little bit similar thinking to what we did the first day of classes with the cones and the cylinders. Okay? So now we understand. So what happens then is that if I happen to stand on this plane here, then the second contribution is going to be 0, and then all those points here, when I make an observation, it's going to have an electric field pointing in which direction? Just along P. Yeah?
No, because when there's no P, when you're on that plane, then you're just really going outward from the dipole.
No, when I am on that plane, again, there are two terms. This term that points in the P direction never cancels. There is always going to be a term that goes along P. So if P is vertically up, that first term always exists. It just drops away with distance, but it always exists. The second term, though, may not, because I have a scalar product. So for the points that are on that particular plane, perpendicular to P, they are going to be 0. Okay, so the conclusion is that this picture, now we can enhance it a little bit. This term here is always going to be some value that depends on the distance, but this vector here, actually, as I change this angle, and I make it smaller and smaller and smaller and smaller, then this magnitude will shrink to 0. It will be maximum when P and r minus r prime are aligned. So when I have points along the line of P, this scalar product is going to be maximum, and when I am on that perpendicular plane, it's going to be minimum. Okay? So I think that's sort of everything that we can say about what's going on with this electric field. Okay? The next best thing besides talking is to try to make a plot in the computer. Okay? So I didn't give you, I gave you a new homework today, but I didn't include this thing. So I think it's something for you to do on your own. Okay? There is enough homework at this point. Okay. So let's change pace a little bit. I need to return to the so-called multipolar expansion, but so that we don't get bored with these things, let's change pace a little bit, and let's consider something else for a few minutes and then we'll return. Okay, we'll need that result anyways and we can do it. Let's consider Gauss's law that all of you know. All of you know Gauss's law, and you've used it in freshman physics for computing some electric fields of high symmetry. Okay, like for example, if you compute the so-called flux of the electric field on a surface, then that can be useful to compute the electric field of a point charge, of a sphere, of lines of charge, etc., right? But it turns out that all those examples that we learn, all of us learn in freshman physics, are really very unrealistic. Okay, that's not the real power of Gauss's law. Okay, you can actually compute the electric field of those very simple configurations, but you can also do it directly by integration. And whenever the problem has no symmetry, then you cannot use it anymore to compute electric field. So what I'm trying to tell you, the message is that don't think that Gauss's law is a way to obtain electric fields in an easy way. That's not true. But it is very powerful result in other ways. So we are going to prove it, and what I'm going to say is that the result that we are going to get when we write it in a differential form, not in an integral form, then it's going to help us to solve electrostatic problems that couldn't be solved otherwise. Okay, and to advance, what I'm trying to get at is that so far we've solved electrostatic problems assuming that we know where the charges are located. So, for example, we did the line of charge, we did the disk of charge, the ring of charge, we did dipoles, etc. We've been studying, and even the problems that you've done so far in the homework are of that type, that they involve summing of configuration of charges to obtain the electric field or the potential somewhere. But what happens if I have a material, okay, a chunk of stone, may have some pieces of metal, plastic, I don't know what it is, and then I bring some charges that I may know what they are, very close, and the material reacts to those external charges by rearranging the charges inside. Clear? That's possible, right? Now, if the object is irregular, most likely I won't know where those charges are, and I'm still interested in obtaining the electric field. So, right? And so, are there ways to solve for electrostatic potentials and fields without knowing where the charges are? And it turns out that there are very powerful theorems that we are going to learn soon that will help us. But one of the first things we need to do to start understanding that is to understand Gauss's law. Okay? And so first we are going to prove Gauss's law in a very general way. You know the statement, of course. Yeah. The statement, you're going to help me with that, and we'll go from there. So what is the statement of Gauss's law? The charging is closed, eh? Yes.
The integral of EDA.
Exactly. Okay. Okay. So this part is okay, and this should be inside, of course. Is equal to the electric field times the area, but more specifically, in a general situation, how do we write that?
Integral of EDA. The integral of EDA.
Okay, perfect. Okay. Is the integral of E, we call it ds, same thing that you are saying. Okay, so even more, so far, okay. Let's make it a little bit more general. It is a surface integral, sure, yes. It has to be an enclosed surface because otherwise we don't have charge inside. And what else do I need to just finally fix it completely? The dot product, right. So it is this. Okay, so that's the full statement. Okay. So let's show how that works, and also why, if the charges outside don't contribute to the field, and then the implications of that thing. But let's do a little preliminary to think about. Okay, something that you already are familiar with. So I want to recall a result of how we deal with objects that are proportional to each other. So let's start with lengths. Okay, so let's suppose that I have a point. Let's consider a planar problem first. Okay, I have a point in the plane, and then I have two lines that pass through that point. Okay, and then I consider two lines like that. Okay, and so if I have that construction, I can write immediately all sorts of ratios that are constant. So for example, let's say that I call this point A, and this point B, and this point A prime, and this point B prime, okay, because sort of they are equivalent, okay? So for example, the distance from O to A divided by the distance from O to B is equal to the distance from O to A prime over the distance O to B prime. All of you know that, okay? So, yeah, I forget what, yeah, there is a name, yeah. You should remember more than me, because this is high school stuff. And so, okay, so there are other things that you can do, right? I mean, like the ratio between OA prime to OA should be equal to A prime B, AB, and so on. There are many things like that that you can do, right? Okay, right? Okay, so of particular interest, let's say that I do another line, although it's not necessary, but let's say that I do this one, and then I define a point C and C prime, okay? So then we are interested in this thing. So for example, the distance from A prime to B prime divided by the distance from O to C prime is equal to the distance from A to B divided by the distance from O to C. That's another one that I can write. Okay?